Welcome, ladies and gentlemen. Today I would like to show you the presentation which is called Dynamic Simulation of Binding and Diffusion of Helium in Calcium, Strontium and Barium fluorides. I would like to thank you all for attending this presentation. I plan to be brief. First, I would like to talk about presentation plan. As you can see, it consists of 4 parts. In this work, I use the molecular dynamics method, an actual study of the mechanisms of dissolution of helium in the crystal lattice, and using the empirical pair potentials reproducing the experimental strong binding of helium to cations in crystals. The systems studied in this work were model crystals of octahedral form isolated in vacuum. At the beginning of a computational experiment, single helium atom was placed in one of the central intermediate positions. All the particles moved according to the Newton's equations of motion that were integrated by the leapfrog method. The helium diffusion coefficient was determined from the Einstein relation, and interaction of the particles was modeled by using the empirical pair potentials. Averaging the time dependencies of the square displacement of the helium atom over a series of computational experiments made it possible to determine the diffusion coefficient corresponding to a given temperature. The plots of atomic coordinates during the diffusion jumps demonstrate the interstitial mechanism of helium diffusion with a direct transition of atoms between adjacent equilibrium interstitial positions. The atom moves from one interstitial position to a neighboring one, remaining in the same plane. It moves almost in a straight line. An alternative could be motion through an anionic vacancy. However, such motion was not characteristic for the considered model systems. The activation energy of interstitial diffusion was obtained as the slope of the dependence of the frequency of diffusion jumps on the reciprocal temperature in the Arrhenius coordinates. In the present work, we obtained the corresponding graphs shown on the slide. The calculations were carried out in the temperature range from 1050 to 1300 kelvins, excluding the superionic region. This brings me to the end of my presentation. The diffusion activation energies are overestimated in comparison with experimental data and static calculations, which is due to the underestimation of the energy in interstitial dissolution. And for the correct dynamic modeling of the considered systems, it is necessary to use many particle interaction potentials. One can't but mention the straight lines obtained. The Arrhenius coordinates indicate the prevalence of the interstitial mechanism of helium diffusion in the entire temperature range studied for all 3 crystals. Thank you for listening, and now if there are any questions, I would be pleased to answer them.